Welcome to the MOSOMIC MEMS Microphone Guide. My name is MIKKO Suvanto. In this episode, I'll continue talking about the mechanical implementation of MEMS microphones into devices, the space the implemented microphone takes in the device, the placement of the microphones within the device, and mechanical protection of the microphones in the device. Stay tuned! This series is sponsored by Innovating Technologies. In many cases, especially in portable devices, the space taken by the microphones in the device is a critical factor. Depending on the case, the key parameter may be the overall volume the microphone takes, or the critical thing can be, for example, the thickness or width of the space needed for the microphone. Size is, of course, especially important in very small devices, such as wearables like watches. The size or thickness or width of a microphone implementation doesn't depend only on the size or thickness or width of the microphone. The way the microphone is mechanically implemented into the device plays a big role too. The implementation depends on the package type of the microphone. The two types commercially available at the moment are bottom port and top port microphones. In some cases, a side-ported microphone could be a good solution, but they are not available at least yet. Sealing a side-ported microphone could be challenging, and the resulting implementation might actually end up being bigger than the implementation with a top or bottom port microphone. The choice between a top port and bottom port component depends on the mechanical structure of the device and the location of the microphone in it. Like I've explained in previous episodes, the best solution in terms of performance and reliability of the microphone system is to have dedicated sealed sound ports for all the microphones. The need for a sealed channel is a key factor that affects microphone implementation sizes. Luckily, the preference what comes to both the acoustical performance and implementation size is the same. The sound channel should be as short as possible. The sound channel of a bottom port microphone starts at the bottom of the component at the sound port and goes through a hole in the device circuit board. On the side of the device circuit board on which the microphone is on, space is needed only for the microphone itself and a small safety zone around the component. The width of the keep-out zone depends on what components or mechanical structures are around the microphone. If there are only other surface-mounted components around the microphone, the safety zone only has to be wide enough to allow safe assembly of the components onto the circuit board and enough distance from one contact pad to the next one on the circuit board to prevent accidental solder bridging between pads. If there are mechanical structures other than surface mount components next to the microphone that may move in relation to the microphone when the device is handled or dropped onto the floor, the safety zone must be wider. It has to be wide enough to make sure the adjacent mechanics cannot touch or hit the microphone and thereby cause harm to the microphone package or its solder joints. On the other side of the device circuit board, space is needed for sealing and the acoustic channel that connects the microphone to the surface of the device. The space needed for the channel naturally depends on its length and shape. The sound channel of a top port microphone is sealed against the sound port on top of the microphone, or in some cases there can be a sealing boot that goes around the microphone. Sealing a top port microphone only on the top is naturally a better solution what comes to the footprint area of the implementation. However, if the microphone is very small, there may not be enough surface area on the top for reliable sealing. In this case, a sealing element that reaches also around the component may be the only feasible solution to make sure that the sealing area is adequate and that the sealing element stays firmly in its place. It should be noted that in this case there should still be sealing material also on top of the component so that the sound channel is only a small tube. Otherwise, a relatively big cavity may be formed into the sound channel, causing a Helmholtz resonator that will impact the frequency response of the microphone system. The notable thing here is that the size advantage sought with a small top port component may be lost if the sealing has to be done also on the sides of the component. A smaller component may also have a poorer performance than a slightly bigger component if the size of the back volume has been compromised to achieve the smaller size. Therefore, it should be carefully considered whether the smallest possible microphone component actually makes sense or not. A keep-away zone is needed also around the top port microphone. A benefit of a top port microphone is that it requires space only on one side of the device circuit board, unlike bottom port microphones that take space on both sides. Sometimes the sound port doesn't point up or down from the microphone but to the side. These are sometimes called side-firing solutions. They can be achieved with a bottom or top port microphone and a sealing boot that includes a bend in the sound channel running through it. Okay, let's switch over to talking about another key mechanical implementation factor, the placement of microphones in the device. The locations of the microphones in relation to several things can make a big difference to the sound quality and reliability of the microphones. The surface of the device, the corners, edges and flat surfaces on the cover of the device, the other microphones in the device, noise sources within the device. The noise can be acoustical, electrical, electromagnetic, as well as vibrations. Heat sources, the locations of the sound sources that the microphones are meant to capture, the locations of the ambient noise sources that the microphone system wants to avoid capturing, and sources of mechanical stress. I'll talk about each of these in more detail next. Firstly, the distance to the surface of the device affects the length of the sound channel. Therefore, it can affect the frequency response of the microphone significantly. The closer to the surface the microphone is, the shorter and better the sound channel can be. The actual length of the channel naturally depends on its shape and the location of the sound port mouth on the surface of the device. The features of the device housing, corners, edges and flat surfaces affect the propagation of sound. They can, for example, affect the directionality of a microphone or a microphone system, or cause unwanted changes in signal levels. The impact of these effects depends on the location of the microphone and the location of the mouth of the sound port on the cover of the device in relation to the corners, edges and flat surfaces. The impacts also tend to be very dependent on the frequency of the sound. Placing a microphone and its sound port in the middle of a flat surface is likely to cause a boosting of some frequencies, as the incoming sound reflects from the surface and, at some frequencies, amplifies the signal. The amount of boosting and the sound frequencies of the resulting changes in the frequency response of the microphone depend on the size of the surface. Another thing to take into account with large flat areas is that, unless reinforced well, they tend to deform or vibrate easily. A deformation can cause changes in the acoustics of the microphone sound channel, thereby causing changes in frequency response, as well as handling noises or other issues. A vibrating surface can also cause audible noise. The distances between microphones in a multi-microphone device and their locations relative to each other in the three-dimensional space can affect the functionalities of microphone arrays. The optimal locations of the microphones, or the mouths of the microphone sound ports on the surface of the device, and the distances between microphones are often dictated by the processing system that receives the output signals of the microphones. There can be big differences in microphone placement requirements between different processing systems. For example, some two microphone noise cancellation systems require that the two microphones are placed so that a line drawn through them points at the wanted sound source. Then again, some systems want the microphones to be placed so that the line between them is perpendicular to the direction of the wanted sound. The latter configuration is typical in laptops, where there are often two microphones side by side at the top of the display bezel. For stereo microphone pairs, the two microphones should be placed symmetrically in relation to the center of the device to make the stereo sound image as symmetrical as possible. In a typical two-microphone stereo system made with omnidirectional microphone components, also the acoustic distance between the two microphones should be maximized. Signal processing techniques that artificially enhance the captured stereo can be used to improve the stereo image. For systems that record more than two channels, for example 5.1 surround sound capturing systems that use for example 3 microphones, the optimal microphone configuration depends on the processing system that creates the multi-channel signal. The placements of the microphones or their sound port mouths on the device can also cause an effect known as comb filtering. I won't go into detail about comb filtering now, but I may visit the subject in another video. Let me know if that's something you'd like to learn about. Microphones should be placed as far as possible from noise sources within the device. The noise source can be acoustical, electrical, or electromagnetic. The loudest sources of acoustical noise are often the speakers or earpieces of the device. The speakers can be operational, blasting loud content, while the microphones are simultaneously capturing sound. In addition to physical distance, good acoustic sealing and well-functioning echo cancellation systems are the best ways to cope with the noise from the speakers. Other sources of acoustic noise can be things like camera actuators, keypads and buttons, electrical components that cause acoustic noise, as well as handling of the device by the user. Also, any vibrations in the device, such as those caused by vibration actuators, are potential noise sources for the microphone. Electrical noise can be caused by, for example, switched power systems and RF power amplifiers. It's of course important to minimize the amount of noise those components generate and to filter the noise that appears on sensitive signal lines, but it often helps to also put some distance between the noise source and the microphone and its signal lines. In wirelessly connected devices, antennas are the typical source for electromagnetic disturbances. In a modern multipurpose device, such as a smartphone, there can easily be 4 microphones and more than half a dozen antennas. It's practically impossible to avoid having to place a microphone close to an antenna, but sometimes even very small differences can matter. 4 mm between a sweet spot of an antenna and a microphone is better than 2 mm. Often, the electromagnetic waves turn into electrical interference in signal lines at some point, so the same methods of noise reduction, mainly filtering, help as with electrical noise. Heat can cause microphones to change their sensitivities, and this can cause problems with, for example, microphone array system performance. If only some of the microphones in an array get heated because they are located close to heat sources, such as power amplifiers, the sensitivities of the microphones in relation to each other change, leading to decreased algorithm performance. Therefore, it's a good idea to put some distance between microphones and heat sources if possible. It also helps to choose microphones that don't change their sensitivities significantly with temperature. When placing microphones in the device, it's important to take into account the locations of the wanted sound sources you want to listen to, and also the locations of the sound sources you want to suppress. The wanted sound source can be, for example, the mouth of the person using the device. In some cases, the direction of the wanted sound is known, but more and more often devices are used hands-free or on a table, and the direction of the wanted sound source is not predetermined. The directions and distances to the ambient noise sources are also often not known in advance. Some ambient noise cancellation systems operate on the principle that there's a microphone close to the wanted sound source, for example the mouth of the user of the smartphone, and another microphone as far away as possible from the wanted sound source listening to the ambient noise. The noise is then subtracted from the wanted signal, the signal of the microphone that is close to the source. In this case, the locations of the microphones are dictated by the operating principle of the noise reduction system. Ergonomics are also important to take into account when placing the microphones. The microphone should be ergonomically placed so that it's in a convenient place when the device is used, for example, close to the mouth of the user. Also, accidental blocking of the microphone sound channel should be avoided. The object blocking the sound port can be, for example, the hand of the user, or a tabletop the device is placed on. All use cases, such as calling with the handset on the ear, hands-free call, conference calling, as well as video recording should be enabled. In video recording, one must take into account both landscape and portrait positions, and the possibility of the wanted sound signals coming from the front of the camera as well as from the back if the camera operator narrates while filming. There are also other use case related variables that affect microphone placement. For example, the direction of the incoming wanted sound signal, the direction of the sound signal that should be cancelled, the distance to the wanted source, the distance to the disturbance signals, and contents, for example frequency spectrums, of both the wanted and unwanted sounds. Finding the optimal location for the microphones may be challenging if the device is used in many different ways and for different purposes, like for example smartphones are. Typically, it's a good idea to ask the supplier of the noise cancellation system used in the device for guidelines on microphone locations. Lastly, microphones should be placed so that they will be subjected to mechanical stresses as little as possible. Any points in the device where the user physically interacts with the device, such as physical buttons, can be sources of deformations and stresses. Locations close to screw towers or high-stress points on circuit boards may end up under stress when the device is assembled. Such stresses may cause deformations of the circuit board the microphone is soldered on, or changes in the dimensions of the sound channels. Okay, it's time to talk about the role mechanical implementation plays in protecting the microphone. First of all, the job of the mechanical implementation of a MEMS microphone into a device is to minimize the risk of problems caused by contamination. The structure of a MEMS microphone is open and more or less vulnerable to contamination. The implementation should prevent the traveling of contamination through the microphone sound channel in the device mechanics. The ingress of solid types of contamination, like dust or sand, can be prevented with dust meshes. There's a variety of meshes available, differing in how they're manufactured, their density, and the evenness of their structures. Weatherproof membranes can be used to stop also liquids from getting into the microphone. Depending on the specifications of the membrane, it can be completely watertight, enabling the immersion of the device for a long period of time without the risk of contamination getting into the microphone. Other membranes are water resistant, keeping splashed liquids out of the microphone and possibly protecting the microphone in the case of rain or shower, but not immersion. The mesh or membrane can be added into the sound channel in several places. The assembly of a protective element can be challenging because the meshes and membranes tend to be limp and challenging to handle with automated systems. Including the element in another component, such as a sealing gasket, makes it easier to handle and assemble the protection into place. If the protection cannot be included into another component, it might make sense to include a rigid element, such as a washer, into the protective element to make the structure easier to handle. The protective element can also be included in the microphone package. A mesh or membrane on top of a top-port microphone might make the acoustic sealing of the sound channel difficult. Therefore, putting the protection inside the package is a safer option, though this may make the microphone more challenging to manufacture. If the mesh or membrane is included into the microphone package before assembly onto the device circuit board, it naturally has to withstand reflow. The protection level of a mesh or a membrane in the microphone sound channel can be given as an IP value. IP is an IEC standard and stands for International Protection Marking, sometimes referred to also as ingress protection. The rating code starts with the letters IP and is followed by two numbers. The first number rates the solid particle protection and the second one gives the liquid ingress protection rating. For example, Ep16 means that a smartphone is dust tight and that the device is suitable for continuous immersion in water 1 meter or more deep. The IP rating is measured with a set of tests outlined in the IEC standard 60529. The more protective the mesh or the membrane is, the more likely it is to affect the sound that travels through it, and thereby the performance of the microphone system. A membrane or mesh that blocks particles or liquids effectively is likely to be a significant acoustic resistance. As I explained in episode 3, acoustic resistances cause noise and thereby increase the noise level of the system. The protection can also affect the sensitivity and frequency response of the microphone system. A mesh or membrane can dampen especially higher frequencies. The system can benefit from this in cases where there are acoustic resonances at higher frequencies. The mesh can reduce the heights of the resonance peaks. An acoustic resistance in the sound channel can also dampen acoustic shocks, such as the ones caused by ESD sparks. This may be a significant factor protecting the sensor element from shocks. In an ideal case, the protective mesh or membrane would be acoustically transparent, meaning that it doesn't affect the sound traveling through it. But in the real world, a compromise may have to be made between protection level and acoustic performance. It should be noted that, in some cases, a dust mesh may just move the problem away from the microphone but not prevent it completely. This is the case, for example, if a large quantity of contamination, such as lint, ends up in the sound channel. Even if the lint stops at the dust mesh, it can still block the channel and cause changes in the frequency response, for example high frequency attenuation or reduced sensitivity. Another task for the mechanical implementation of a MEMS microphone into a device is to protect the microphone from abuse and other external factors. Abuse can be things like touching, poking, squeezing, as well as mechanical shocks. Putting the microphone inside the device covers already provides some level of protection. It prevents touching and poking of the microphone, except for thin or sharp objects possibly inserted through the sound port on the surface of the device. The device provides also protection from direct impacts. To maximize the protection, it's important to design the device mechanics around the microphone so that impacts to the outside of the device aren't conveyed by the device mechanics to the microphone. There are some things that help keep the microphone safe, even in the case of a hard impact, such as the one the device faces when dropped onto the floor. Rigid enough mechanical structures around the microphone, including supporting structures if necessary, prevent deformations. Good support structures on the device circuit board prevent uncontrollable flapping or whiplash of the board. Another way to protect the microphone is to have buffer zones around the microphones to prevent adjacent mechanical structures or components from hitting the microphone if the device is deformed by an impact. Typically, there are limits to the pressure allowed to be applied on a microphone package. Also, the solder joints and the circuit board under the microphone should not be stressed unnecessarily hard. Therefore, it's important to design the device covers and body so that pressure applied on the cover does not get directly coupled to the microphone. Okay, that's it for this episode. In episode 17, I'll go into the electrical implementation of MEMS microphones into devices. I'll start with the implementation of analog output microphones. I hope I'll see you around. Cheers! If you have any comments or questions, write them down in the comments below and I'll do my best to answer them. You can also contact me online or on social media. If you like what you saw here, give a like for the video and subscribe to the MOSOMIC channel. That way you help me reach more people and thereby create more content. If you need more in-depth microphone training than what you saw here, contact me and we can arrange it. The training can be adapted to suit any interests and skill levels, and the customer can choose the location and duration of the course. MOSOMIC provides also consultation services in all things related to MEMS microphones. If you're a microphone buyer, I can help you select the right components for your product and manage your microphone suppliers. I can also assist in implementing the microphones into your device. For microphone manufacturers, I provide microphone marketing, product definition, product management, and development management services. I can also help you create all kinds of MEMS microphone documentation,